All right. Now, if you didn't manage to join it, that's okay. It'll come up again. Okay, so this time we're going to be working on gases. We are going to be gassy. I know. Thank you for the slight laugh. All right. So, respiratory therapist assesses treat a range of patients. They perform a variety of diagnostic testing. This is going to be including measuring breathing capacity, concentrations of oxygen, carbon dioxide in the patient's blood, as well as finally pH levels as well. Now note that when they're doing these respiration treatments and measurements, that the formulas they use are actually surprisingly simplistic for most of these things. And you're going to learn the base formulas that you can actually understand these things. Okay? Now, has everybody done that before? Had to breathe in the machine. It measures how much you can breathe. Okay. How much force is behind your exhalation. Okay, so we all live at the bottom of a sea of gases or a solution of gases. This is called the atmosphere. It's that stuff around you right now. You can feel it if you move your hand back and forth. Yes, that is the atmosphere. You cannot see it very well. You can see it at a diffraction angle. That's what the sky is. O2 is 21% of this atmosphere. This is the gas that's probably the most important to life processes on the planet. It is what we're breathing right now that we're depending on to get our energy, right? Okay. Did you guys know plants also use O2? Yeah? Fantastic. Yeah, so plants also use O2. Uses both CO2 and O2. So our atmosphere is 78% nitrogen. So the next time you see a sci-fi movie and they go, Planet X has a nitrogen atmosphere, it's poisonous to us, what are you going to say?
No, it's not.
No, that's ridiculously stupid, right?
Technically true, but not right either. Because
No, not
oxygen does take us apart after long enough.
the nitrogen.
Use it.
The nitrogen doesn't harm us at all. Our atmosphere is a nitrogen atmosphere. It's the majority nitrogen. So we live and depend on a nitrogen atmosphere. In fact, if our atmosphere was too much oxygen, it would actually oxidize us. And things that shouldn't be bursting into flames would burst into flames. Yeah. That's why they don't do space stations and submarines with 100% oxygen. It's actually incredibly dangerous. And that's why they usually don't put gas tanks when you're scuba diving as 100% oxygen either. That's actually quite dangerous. Okay. So our atmosphere is a nitrogen atmosphere. It's 78% nitrogen, right? The vast majority of it is nitrogen. Notice that once we account for the oxygen and nitrogen, how much of the atmosphere is accounted for? 99%, yeah. So the rest of the atmosphere is 1% or less. Okay? That includes things like ozone. Anybody ever heard of the ozone layer? Okay. So the ozone layer is simply the ozone that happens to mostly be in the upper atmosphere. The other place where there's a high concentration is actually down here at sea level-ish. Okay? And that ozone is actually generated by high energy light hitting the oxygen in the atmosphere. That generates a reaction making the ozone. It then is heavier, so it drifts down into a layer we call the ozone layer, where it again gets hit by another form of high energy light, and that causes it to break down into oxygen again. Okay? That cycle is what we call the ozone layer or ozone shield. We actually put a chemical in the atmosphere by accident that broke that ozone layer down without it doing it light, capturing the light it should have. And if we were to interrupt that cycle and cause it to stop working, we would actually have high energy UV light coming down to the surface of the planet. This high energy UV light would give you a tan in under a minute. It would give you sunburn in anything over a minute. and it would kill you in about 10 minutes. And so we actually did come pretty close, way closer than we should have, to wiping all life out on the planet. Okay? It would have literally killed all the plants, animals, everything. Bacteria, everything. Everybody's aware at a hospital you use UV light to sterilize things, right? Yeah. That's the same sort of UV light that the ozone absorbs. So we would have destroyed all life on the planet down to about a meter or so in the ocean. Okay? Nothing could have lived on the surface.
What about below that? Would that been fine below that?
Yeah, about 3 meters, it probably wouldn't have been affected too much.
Does that mean that since there was still life to continue other biological processes under there, that maybe eventually, due to those processes giving off gas, the world could eventually work itself?
Yep. The world would have definitely eventually evolved organisms that would be more resistant to UV radiation, and we will repopulate, but it would have taken like billions of years, right? It would have been a long period of time, or at least hundreds of millions of years, probably.
Now I'm wondering about
Also, the caves would have been safe. Yeah.
How many people actually live in caves?
Not a lot, but there's entire ecosystems in caves. So, yeah. Other gases include things like argon, CO2, carbon dioxide, which you all know in exhaustive detail now because it's very famous due to global warming, right? And then water vapor, which you all know because you live in Tennessee. Now, I will point out one little thing. Does anybody know what causes the majority of global warming? It's not CO2.
Carbon monoxide stuff from cows.
No, it's not a pollution. It's not methane. It's not carbon monoxide. It's not any of those things. I've actually given it to you up here.
Nitrogen?
Nope.
Oxygen?
What if it was nitrogen?
Yeah, that would be wild. There wouldn't be any global warming because it would already be as much as we're going to get. But,
Oxygen?
nope, not oxygen.
Hot air rises.
Ozone.
Water. Water is about 2/3 of global warming. Why is it never talked about? Well, you live in Tennessee. What the heck can we do about the water in the atmosphere? Not a lot, right? So nobody ever talks about the water because there isn't really anything we can do about that. Okay? But yeah, it's the majority of global warming is water, actually. Yeah. Interesting enough, O2 and N2 do not actually absorb in the infrared. They don't cause the greenhouse effect. Okay? It's actually things that have polar bonds that cause greenhouse effect. Yeah. Interesting, huh? Look at that. You know enough to actually understand a bit about greenhouse effect. We will talk a little bit about that, but I won't get time to really go into it, unfortunately. Kinetic molecular theory. So a gas consists of small particles. They move rapidly in straight lines. They have essentially no attractive or repulsive forces. These are all tenets of kinetic molecular theory. They're very far apart. They have very small volumes compared to the volume of the container. You can think of them as super tiny particles. If we were talking something like a football field, they would be far, far smaller than marbles. Okay? And so if you have millions of marbles on a football field bouncing around, are they going to interact much? No. Because they're just so small, right? There's very good chance they never will hit each other. So you got to get a lot of gas to actually have any interaction with itself. Okay? They have kinetic energies that increase with an increase in temperature. Does anybody remember what an increase in temperature is? That definition I gave you is different than your book.
Increase in temperature is the
It is increase in temperature actually makes you go out over the activation energy faster, but because you jump over it better. But what an increase in temperature is it's randomized kinetic energy. Okay, so you can think of it. Has everybody played that game where you have the little tiny beads or marbles in it and you tilt it different ways?
Yes.
And you try to get them in the holes? Okay. and you got pissed about it, and eventually, right?
I always liked the game.
Did you?
Yeah.
Oh, fantastic. Then, anyways, if you shake it, you can think of that like the randomized kinetic energy and temperature, okay? So if you have a low temperature, you're shaking it very gently. If it's a high temperature, you're shaking it a lot harder. Okay? And so your overall randomized kinetic energy goes up. All right, so these are some of the properties that describe a gas. We have pressure, we have volume, we have temperature, and we have the amount. Note that the amount is the N. See that N symbol? Lowercase n. Note that if you put M, that would be meters, wouldn't it? And so we don't put M for the amount, even though we're going to be using moles almost exclusively for that amount. Okay? It's also going to be the last thing I'm going to talk about, so keep that in mind. Most of the gases I'm going to be talking about are sort of a fixed amount in there. Okay? And that's what I'm going to be worrying about first, and then we'll go into amounts. All right. Okay, so let's talk about the volume. Typically, this is going to be in liters or milliliters, though for whatever reason, atmospheric science likes to use meters cubed. So if you start looking at like CO2 amounts in the atmosphere and all that stuff, they have a tendency to use tons or gigatons, which actually kind of makes sense because it's large amounts, or meters cubed, which doesn't make any damn sense because it doesn't fit with anything else. But the reason they like using that is actually a math reason. It makes the equations a little easier, which isn't really a factor because they usually computerize it anyways, but yeah, it's a thing. Anyways, typically you're going to look at liters and milliliters. Again, this is going to be the volume of the container is going to end up being your volume of your gas. If you're in a container like this, which is open, then that's the volume of the planet essentially, right? That's our container right now. So an increase, it's going to increase with temperature at a constant pressure. So if you were to, anybody taking a balloon out when it's really cold?
I can't think of any memories off the top of my head.
Okay. Anybody? How about a like acetone can? You guys have used like paint thinner. When it's hot, you put the cap on. You put it in the garage. It's cooler now, right? Okay. What happens to the sidewalls to that? They suck in. The volume gets smaller, doesn't it? Okay. Same thing happens with a balloon. If you take balloons out into cold weather, you're going to see the balloons shrivel, right? And they look sad. And then you bring them into the warmth again, and what happens? They expand back out, right? Yeah. All right, so the temperature of the gas is going to relate to the average kinetic energy of the molecules. It's going to be measured in Kelvin. And these problems we're always going to have to be in Kelvin because that's an absolute temperature scale. Okay? If we're in degrees Celsius, degrees Fahrenheit, that's going to cause us problems. Okay? We also can't just ignore those units. So one of the things I need you to stick in your head right now and get stuck there, you're going to have to convert all temperatures to Kelvin immediately. Okay? If you're working in anything but Kelvin for temperatures, got a problem. All right? And the reason for this is how do we convert Celsius to Kelvin? Plus 273, right? Notice that as a plus. That is not a multiplication, is it? Every other conversion is a multiplication, isn't it? Except for the temperatures. The temperatures always have a damn plus in them. Okay? So, when the temperature of the gas decreases again, molecules are going to have fewer collisions. If they're colliding around less, then you're going to have less volume of them. Has anybody ever seen a mosh pit?
Yes.
Yeah? No? Okay. So when everybody's colliding around, they take up a lot more space, right? When everybody just stands there quietly and listens to the music, you can pack a lot more people in, right? They take a lot less space. Or you could also think of it as Black Friday sales. Everybody's seen Black Friday sales, right? when they're all lined up quietly before it opens, they take up very little space. And then they start fighting each other over the deals, and they take up a huge space, right?
Way before COVID.
Yeah. I mean, they're still a thing, but not like they were before then. Yeah, they were.
Did their 7-8 hours early.
Yeah, I never really understood them. I'm like, the online has just good deals. Yeah. All right, so pressure. You're feeling the pressure now. So pressure is going to be a measure of the gas particle collisions with the sides of the container. It's measured in units of millimeters of mercury or torr. Millimeters of mercury and torr, the same unit. For whatever reason, when they changed it so they're no longer using columns of mercury, they changed the unit's name as well. Because it's a torsion meter, technically, I guess. But, yeah. Anyways, millimeters mercury torr. You've probably all seen that at some point in their life. If you haven't, then there it is. Okay? Atmospheres. This is probably the most common unit that's used by scientists, is atmospheres. Guess what the pressure of the planet's atmosphere is? 1 atmosphere. I know, right? They took the average pressure of the planet at sea level and they made a unit of it. Okay? And that is the atmosphere. So we have pascals and kilopascals. And then we have pounds per square inch. And this is probably the one most of you have actually encountered the most because it's used a lot in like cars and stuff, right? You can also see cars done in pascals and kilopascals, by the way. If you look carefully at your tire, it actually has those on it. So, usually. Yeah. Gas particles in the air are going to exert pressure on us. This is actually called atmospheric pressure. And what atmospheric pressure is it's not actually a column like your book says. It's more of a cone above you. But all of the gas above you is going to be pushing down on you. And then once it hits the ground, it pushes down on the ground, right? And then splashes out to push on the sides. Okay? Now, you don't really feel this right now because you're being pushed every way equally, okay? So if you just sort of sitting here right now, you're not feeling the atmospheric pressure, are you? That's because, has anybody ever had somebody hold on to their hand or their arm for long enough that you stop feeling it? Yeah. Yeah, you can have that happen too. You stop feeling things when they're sort of equal and they just don't change for a while. Okay? And that's what you're doing right now with the atmosphere. It's pushing on you equally in every direction. If you take your 2 hands, press them together to make all the gas come out between your hands, and then try to pull them apart, do you know what you're feeling?
Suction.
Suction. What is suction? It is when you have a vacuum, the gas is trying to push in towards it, right? So what you're actually feeling is the atmospheric pressure. That's what's causing suction. Okay? And you can do the same thing with your cheeks, obviously. Right? And that is actually the gases around you, the atmospheric pressure, pushing in right now. Okay? Do you know how much pressure you can generate with suction? Up to 1 atmosphere. I know. Anywhere from 0 to 1 atmosphere. That's what you can do with suction. Yeah. Anybody ever seen Futurama, by the way? Great movie. There's a scene in Futurama where they're going down into the ocean. They're taking a spaceship down into the ocean, and the people are going, "Professor, what is this ship designed to handle for pressure?" And he goes, "Anywhere from 0 to 1 atmosphere." And they're going 10 atmosphere, 100 atmosphere pressure, right? Down in the ocean. So it crushes the ship, of course.
Is it a cartoon?
Yeah, it is.
Okay.
Yeah. Which is exactly true. Spaceships are designed to handle between 0 and 1 atmospheres. Yeah. The big thing they're designed to do is not let gases out, which would cause your spaceship to cool.
how many atmospheres? That makes me think. If atmospheres increases, you go down. How many atmospheres are submarines designed to handle?
Usually, actually, we got a Navy guy right here. Come on.
Nah, I don't do subs.
Okay, that's fair.
Not a chance in hell. I would never call myself. New characters.
As far as I remember, it's somewhere in the like 50 somethings, because they're not handled to do like Mariana Trench.
Yeah, not even close.
Yeah. It's the tens of atmospheres of pressure. It depends on the sub, I believe. Like there are ones that are designed for not going that deep, and ones that are designed to go much deeper.
Yeah, the gym goes deeper than the keep.
Yeah.
If it was me, I think I just had both submarines and spaceships be designed to handle as many atmospheres as I can feasibly make them handle having.
You actually would sacrifice things that the spaceship needs then. Like, to do that, you would have less stopping of leakage of air. And that's more important for a spaceship. Yeah. And then you'd also sacrifice a lot of money. And a lot of the spaceships, it's actually better to pack them down and be able to blow them up. And so they're actually more like balloons. Because it's really hard to get them up in space. But
When we finally get
did you no? Okay. Okay.
That and some just care about how long they can be under the other.
Yeah.
Consistent pressure.
Like it's usually just better to design for the situations they're going to be in and take the edge cases and design those for emergencies.
That's why we do that.
So barometers. Barometers is the old way you measured for pressure. It's extremely effective. And so what you do here is you take a column, you take that and put mercury in it, and it has a vacuum on the other side of it, up here. Everybody see that okay? And then what you do is you put that down into a pan of mercury. And what's going to happen is the atmosphere is going to push down on this pan of mercury, right? And that's going to force that up the column. Can everybody see it okay? Okay. And so, if you're at the normal 1 atmosphere level, that mercury would climb up that column 760 millimeters. Literally, you have a ruler there, it has millimeters on it, and you go 760 up. There we go. Okay? And so 1 atmosphere is equal to 760 mmHg, milliliters of mercury climbing up that column. And that is equal to 760 torr, which is the new unit. And that's because, obviously, we don't want pans of mercury lying around. People have decided that's a bad idea. Which, fair enough. Long term, it is a very bad idea. Short term, it's not really an issue. But long term, it's definitely an issue. And again, that's just the pressure pushing down on this mercury to cause it to climb that column. Now, you could actually do this in inches, couldn't you? You could do this in meters. You could do this in any measurement of height, right? And so you will see there is such a thing as inches of mercury, INHG. You could do it in any units, really. Now, let's talk a bit more about atmospheric pressure. Anybody ever been somewhere very, very high? Yeah. Yeah, like
Colorado.
Colorado?
Not the same.
It was like it was in the Smoky Mountains.
Okay. Yeah, and you're a little bit hard breathing, right? Uh-huh.
I went to a tourist trap called Pigeon Forge once, and we went walking up this mountain. And even though it was fairly warm and completely dry at the bottom, by the time we got to the top, it was cold and actually felt like it was slightly raining around us.
Yep. So the mountains, once you get high enough, I actually lived in Wyoming for a pretty good amount of time. For reference, that's roughly about 5,000-ish feet up from sea level, which is quite a bit higher than any of the mountains around here ever can get. So just the base level that you would live on is higher than the mountains around here. But it's a very different thing. Has anybody heard of athletes training up in the mountains?
Mile High Stadium
Yep.
in Denver, Colorado.
Yep. And they do that because it's very hard to get the oxygen because up in the mountains, when you get higher, you have less pressure coming down on you and you have less concentration of the gases around you. So it's actually harder to breathe. It's going to have less pressure. Like water is going to boil faster and at lower temperatures. Okay? And so it's kind of an interesting thing. This is actually that difference in pressure for a very, very high mountain. And this is why it starts getting very difficult to climb like very tall mountains. Especially things like the Himalayas are very tough. Yeah.
Does that mean all those motivational workout montage things that you see in athlete movies that show them at the very top of mountains and stuff aren't actually just being dramatic? They're actually kind of accurate.
Yeah. Okay, so nowadays they actually have an artificial way of doing this, and it in many leagues is actually against the rules. And it's called barometric chambers. They have chambers that they lower the pressure in. It causes your red blood cells to produce more. And so you actually do get significantly more endurance, significantly stronger once you're in regular conditions.
Wait, why is it illegal? Isn't it like wholly natural? It's not like steroids or anything.
It's kind of like blood doping, where you allow your body to produce and consistently compete at its maximum level.
Yeah. Oh yeah, the Russians always have done it.
They don't even hide it anymore.
No. They've somehow managed to basically like bribe the committee, and yeah.
I can kind of understand that. It sounds like a wholly natural thing if you work out at higher pressure.
It is, but they go past what the natural would be. They go into things that would be like you'd have to be training in the Himalayas to get it, and they even go past that. It gets pretty crazy.
But people live in the Himalayas, don't they? So wouldn't that be natural for them?
Yeah, but it's a bit different. Living there and training there, you'd get it all the time, and so you wouldn't be able to do as much training. But they're only getting it for short periods to increase the blood levels so that they can then do more training than the person in the Himalayas would.
Oh, wait, maybe we're picturing different things. Are you talking about them just staying there and getting their blood more used to the oxygen?
You're not going to be able to get up and down from the Himalayas like it's a long trip.
I was picturing them just staying around that time and training there and then coming back for the contest start. Are you talking about
Yes. Anyways, we need to move on, but they have to travel. There's travel time versus barometric pressures have no travel time. Though I used to actually train up in Wyoming, and I'll tell you, when I came down and like did games and stuff down here in the sea level range, I felt freaking superhuman. It was really messed up. Like my amount of time I could run would 5 times longer. It was just ridiculous. Okay. So right here, some different abbreviations and units for pressure, and those are different ways you can measure pressure, and these are actually the conversion factors, so all of those equal 1 atmosphere. Okay, so all of those would equal each other as well. All right, so again, these are different altitudes and different conditions where you have the atmospheric pressure, and you notice that if you go down deeper, lower than sea level, you actually do get an increase in atmospheric pressure. If you go up higher than sea level, you're going to get a decrease in atmospheric pressure. And you can even very well notice it just on the mountains around here. If you ever get a chance to go to places like Colorado, Montana, Wyoming, or even better, the Himalayas, you will really, really, really notice that difference, okay? Now, interestingly enough, for the temperature stuff, that's a little bit different than just the pressure, okay? The temperature actually falls off as you go up, and then it actually starts going up as you go further. And that has to do with what is being absorbed by the light. So what light is being absorbed at that different level in the atmosphere, okay? Anyways, if you want to talk about that, we can do an environmental class here sometime. All right, so I'm going to ask you a question. What is the 475 mmHg expressed in atmospheres? So join me in the quiz. Make sure you get in here. And then try to figure that out. What would be 475 mmHg expressed in atmospheres.
Crazy scientist?
No. Techno cowboy.
Cowboy?
Mm-hmm.
I have a hat like that. I'm Indiana Jones for my work party.
Hey, this is not actually a costume piece.
No,
This is actually my hat. Stetson.
expensive hats.
Yes.
They're not that expensive.
College student expensive.
Yes.
I mean, they last a long time.
Yeah, I have a Stetson that's like 9 years old.
Mhm.
It was like a $250 hat.
Oh, I did not spend that much on this one. They go on sale fairly often, and if you happen to be in a place where they want to keep their name, you can get them for like less than $50.
What?
Yeah, yeah. Like
My grandpa has
yeah, yeah. So they're not. Yeah, they can be very, very expensive,
Yeah, mine's custom.
but they're not always super expensive. Okay, folks, we're gonna move on. Make sure you get your answer in if you haven't already. And so we got 86% that answered correctly. Yeah, and so what that is we're taking 475 mmHg, we're dividing it by the 760 that 1 atmosphere would be, right? And that gives you the 0.625 atmospheres. By the way, the answer A here is me literally taking that number and putting atmospheres behind it. Yeah, because I'm being tricksy. Yeah. All right, so the pressure in a tire is 2 atmospheres. What is the pressure in millimeters of mercury? Oh, I'm making you work it both ways. Uh-oh. Wicked. Evil, even.
I was kind of expecting you to dress like Don Brown, I'm not gonna lie.
Why Doc Brown?
I don't know, I just get that vibe.
Really?
Well, yeah, I saw that hat was in your office, I'm pretty sure.
Mm-hmm.
I saw your lab coat, I'm like, definitely Don Brown vibes. Like, they just love science and like,
Did you know the
Yeah. No, this is actually my hat. I also have a fedora. Yeah. And this one is from when I lived in Wyoming and Texas and Utah.
or Yellowstone. I can see you dressed like Yellowstone.
Yeah. Yeah. I don't have and I have the right boots. Yeah. You know how you can tell the difference between the different cowboys, right?
By the ones that have the spurs and all.
Yeah, the boots. Yeah. Southern cowboys have the pointed toes
Yeah.
and the heels. Anybody northern or western has just normal work boots like this. Yeah.
Why is that?
It's partially it's to the ground.
Yeah.
Yeah, and it kind of depends on whether you're going to be riding horses or not.
How much you're gonna actually be like? Those are like you're gonna be doing a lot more work on your foot.
Yeah, and you have harder soil. Yeah.
Makes sense.
All right, and that is correct. Good job. So that was just 2 times the 760, right? Okay, folks. The downward pressure on the Hg and the mercury in the barometer is blank, the pressure of the atmosphere.
Pressure is by the atmosphere.
No. Michael Myers? Do we have a victim in this class? Gotta be quiet, yeah.
Quiet like him too.
Good. That's a good one. That's a good costume. Well, Jason, actually, yeah, sorry. But,
We knew it.
it's a good one.
I haven't seen that Jason.
Anybody want to volunteer? Fantastic. Remember? Awesome.
Hold on, give me 1 minute. Stuck by an ad.
Okay, folks. Make sure you go ahead and
Okay, there we go.
very good. He's behind you. He really is behind you, actually. Okay, folks. I'm going forward. So it has to be the same as, right? Yeah. That's actually what we're measuring. It's the atmospheric pressure. And so it has to be the same as. That's what's pushing it up. So the water barometer is 13.6 times taller than the mercury barometer. Why would that be? Why is that?
You can figure out this one just by saying true or false with the answers.
Yeah. Oh, yeah.
Two of them are obviously false if you think about them, so that leaves only one that's real.
It's good strategy for any multiple choice, right?
Yeah.
Okay, folks, I'm going to move forward now. Make sure you get an answer in if you haven't already. All right, moving forward. Okay, so H2O is less dense than mercury, isn't it?
Yes.
So that means that if you have a same weight of H2O as you have of mercury, it's 13.6 times taller. Okay? And that's what we're ultimately measuring, is the offset from that weight, right? Okay, now we're going to be talking about some laws. There's one thing I got to point out. When we're talking about laws, that's different than theories, right? What's the difference between them?
A law can be proven.
A law is being tested every single moment of your life. Okay? Every breath you take is going to be testing these laws right here, okay? Every single one. And so we got lots and lots of evidence to support these, right? Every moment of our lives. Theories, on the other hand, we have a limited evidential base, or we cannot actually test them directly. Okay? So Boyle's law is going to state that the pressure of a gas is going to be inversely related to its volume when the temperature is constant. You're going to notice for each of these laws, I'm going to hold one of these things constant. Okay? Temperature is being held constant here. So if you take it mathematically and represent that, that would be the pressure times the volume of one state equals the pressure times the volume of another state. Okay? So for example, if we half the volume by driving a piston down, we're going to double the pressure. Okay? And again, this is without changing any temperature. Is everybody good with that so far? Okay. You can all experience this if you have a mostly empty bottle. Put the cap on really well so it doesn't leak, and then push down on it. And what you see is as you half the volume, if you get there, you're going to double that pressure, and it's going to resist you a lot, right? You can't actually push it all the way down because it starts resisting you more than your grip strength. Okay? Okay. And so this is actually mathematically, these would all have to be true. So if you multiply the atmosphere's pressure times the volume, liters, then those always have to come out the same number, as long as temperature doesn't change, as long as the amount in there doesn't change. Okay? And again, this is a restatement of Boyle's law. Let's prove this. Let's actually test this real quick, okay? So we got our lungs here. How do our lungs work? We have a diaphragm. We increase the size of that diaphragm. What happens? We draw air in, right?
Yes.
And that's because we have lowered the pressure, haven't we?
Yes.
And so the atmosphere rushes in to fill that vacuum. We push down our diaphragm, don't we? We contract, lower the volume. The pressure inside of our lungs increases and shoots that air out, doesn't it? Okay? And so when we want to pressurize things, what do we oftentimes do? We take our mouth and go, yeah. And we actually exhale out into it, right? To pressurize it. And let's say we want to make a vacuum. What do we usually do? We take a straw and suck in, right? And that's because we are lowering the pressure. We're literally making a vacuum, aren't we? Okay, and so you've all actually tested this law, haven't you? Many, many times in your lives. Ooh. Isn't that great? All right. Okay. And so let's look at Charles' law now. So the Kelvin temperature is going to be directly related to the volume of a gas. Again, we're going to be holding pressure constant and moles of gas constant. So we'll have the same amount for both sides, and we're going to have the same pressure for both sides. So if we were to write this in equation, that would be V1 over T1 equals V2 over T2. Okay? And so we warm this 1 liter container. What's going to happen to that container? It's going to increase, right? Yeah, pressure is going to increase, or volume is going to increase if you allow pressure to equalize. Okay? So if you allow the container to change in size, your pressure stays the same. Your volume is going to double if you double the temperature. Okay? Okay. And you've probably all seen that to some degree. Specifically, you've probably seen that with like a canister. Okay, so now let's look at pressure versus the temperature. So again, this is going to be the higher the temperature, the more the pressure, right? Lower the temperature, the lower the pressure. Have you guys all been to the other side of a compressor? Like the other side of a fridge that is hot?
Yes.
Okay. Or the other side of an air conditioner where it's blowing the air out? Okay. Okay. If you haven't, I can use steam engines from the 1800s. For some reason, that actually has been more successful lately. Yeah, I've seen a steam engine. How have you not been to the other side of the air conditioner? You've seen a steam engine. Anyways, so what you're looking at when you're talking about a fridge or an air conditioner, that's called a compressor. Okay? That's actually what does that. And so when you compress a gas, it increases the temperature. Okay? When you take a gas and let it expand out, it decreases the temperature. Okay? And that's what they're doing. They're compressing a gas, blowing the hot air out away, and then decompressing the gas, bringing that cold air, allowing that coldness to draw the heat from the fridge or the air conditioner. Okay? Okay. If we take all of these laws, we can combine them together. This gives us the combined gas law. Okay? And this combined gas law is this right here. P1 V1 over T1 equals P2 V2 over T2. Everybody good with that so far? Okay. You will have to semi-memorize that. The reason I say semi-memorize, it's pressure volume over temperature. Temperature is the one that's inverse to the other two, so that goes on the bottom, right? Okay. Okay. So again, those are the summary of each of those. That's a Q&A if you need it. So a gas has a volume of 675 milliliters at 35 degrees Celsius, 646 millimeters Hg of pressure. What is the volume in milliliters of a gas at negative 95 degrees Celsius and a pressure of 802 mmHg? In all these cases, because I haven't talked about the moles, the amount of it yet, we're going to have moles constant, okay? I'll get to that in just a bit. You may have heard of the one that has moles in it. That's the ideal gas law. And it's possible you've encountered it before, but maybe not. Okay, now one thing I need to point out here is whenever you have temperatures in here, you always are going to have to convert those to what first?
Kelvin?
Kelvin. You're always going to have to put those in Kelvin first. And that's because those conversions are additions, right? They're not multiplications. They wouldn't cancel out. Okay? Everything else just has to be the same units. So if you want milliliters out of this, you can put milliliters in this. That's fine. Okay? As long as it's the same units on both sides, it doesn't matter what the other units are. So if you want to use mmHg on both sides here, that's fine. If you wanted to use atmospheres on both sides, that's fine. Okay? Because all the units for those are going to cancel out. Doesn't matter. Units for temperatures, those conversions wouldn't cancel out. Okay? So you gotta get it in Kelvin. Okay, so the first thing we do is we convert these temperatures to Kelvin. 35 degrees Celsius, how do we convert that to Kelvin?
Plus 270.
Plus 273, very good. And that gives us 308 Kelvin. The next one, we take negative 95, we plus 273, that gives us 178 Kelvin. Everybody good with that so far? Okay. And so those are our temperatures for this. All right, so the next thing we're going to do is we're going to be using the combined gas law. There's actually two ways you can do this. You can solve the that combined gas law first and then plug your numbers in. Or you can plug your numbers in and then just solve the numbers. Okay? I'm going to show you solving it first so you know how to do that math. Okay? Mm-hmm.
I have a question. I'm not quite good at doing this part in my head real quick. I just want to confirm. 0.800 times 2 would just be 1.600, right?
What are you trying to do?
0.800 times 2.
Times 2 would be what?
1.600, right?
Yeah, 1.604. I think you said 0.802, right?
1.60 what?
Use a calculator. And I need to keep moving on this. Okay, so the next part you're going to do here is you're going to take this equation and get V2 on one side, okay? And how you do this is you can just take both sides and notice that we have P2 and T2 here, right? So we just take both sides, we multiply T2 over P2 to both sides. The hell? Anyways, P2. No idea why that's happening, but okay, notice that that would cancel those out like so. Okay, that would leave you in this equation right here. Now we have V2 on one side. That's what we want to get. That's what we were asked to get right over here. Was the volume in milliliters. We go ahead and plug in our numbers. And so we have V1, which is the volume we were given above. That volume there sets which one's going to be the pressure one and which one's going to be the temperature one, okay? So we look up here. This right here is P1 right there, okay? We put that down here. And then P2 is going to be the 802 right there. Everybody good with that so far? The next thing we're going to do is we're going to take those Kelvin numbers we got before. And so this is the T2 there. That's the T1 there. Okay. Now we just systematically go through the math and do it. Right. And so we take 675, that's times 646, divide that by 802, multiply that number that you get out by 178, and then divide that final number by 308, and that gives you 314. Mm-hmm.
So we could just put all of those like numbers and like plug them in and just do it that way?
You can. Now I'm going to go ahead and work that on the board real quick,
Okay.
because some people find it easier to do each way. It's a sort of random thing, and I never am going to know which way it's going to be. Okay, so the other way you can do this is you can just take this gas law, P1 V1 over T1 equals P2 V2 over T2, right? And you can just plug your numbers directly in there. And so we have a 675 milliliters. That is V1, right? Okay. We have a pressure that's related to that. We go over there, see that 646 up there? Okay. And we put that in. 646 mmHg. And that is P1. All right, we then find our T1, and our T1 is that 308 Kelvin. Remember getting that 308 Kelvin? 273 plus the 35 from before? Okay. Okay, so we take the 308 Kelvin, and that's T1. That's equal to, well, we take the P2, that's going to be the second set of stuff, 802 mmHg, right? V2, we don't have yet, so we gotta leave that alone, don't we? And finally, we're going to get our T2, which is the 273 minus 95, which is 178 Kelvin. Okay. That's P2. All right, everybody got that so far? Okay. And so we're going to then go through and simplify this. We take 802 divided by 178. And can anybody do that number for me? You need to use a calculator. Anybody get out a calculator and do this number for me? This is why I always solve the variables first, by the way. Because it leaves less stuff I have to work out with a calculator.
802 divided by 178.
Yep, 802 divided by 178. 4.5? Okay, and whenever you're doing these, don't round until the very end, okay?
056.
Oh. 4 point what?
56.
5.6? Okay. Okay. Okay, and this is then B2 over here. That equals, and then we would take these numbers, 646 times 675, then divided by 308. 1,415. Thank you. mmHg times milliliters over Kelvin. Okay. Then we're going to divide both sides by this 4.5056 number. This side cancels, and you're left with that. Everybody good with that so far? Fantastic. Notice that if you plug the numbers in before solving it down with the variables, you are in for a bit more work with the calculator. And you have to be more careful about your order of operations with that calculator. Okay? Be very intentional. All right, so we're going to go ahead and move on to the next one. I'm going to make you do this. Ready? Go. It's not any fast deal. I'm going to give you a couple minutes to try to solve this. I will point out that I did not give you every unit the same. Be very careful about your units. Hopefully there's a little voice in the back of your head that sounds like me, I guess, going, be careful with your units. Solve your units. Okay, so a sample of helium gas has a volume of 0.180 liters, pressure of 0.8 atmospheres, and a temperature of 29 degrees Celsius, so that's condition 1, right? At what temperature in degrees Celsius will the helium have a volume? So you're finding temperature. That temperature you're going to find, temperature 2, right, is going to have a volume of 90 milliliters and a pressure of 3.2 atmospheres. Anybody notice something about those volumes? They're different. They can't be different, can they? They gotta have the same units. We're finding the temperature in this one. You plug in everything but the temperature. So we're finding T2. So we plug in everything but T2. Well, the temperature is on the bottom. You're going to use that formula on top.
Yeah, but it's gonna be like on the left and it's like all over.
Yeah, you'll have to solve for that T2. By the way, do you want things to be in degrees Celsius? No, they have to be in what? Kelvin when you work this out. Then you're going to have to, at the end, come back into degrees Celsius, aren't you? Ooh, I was being mean and evil. I made you do extra steps. My goodness. How could I? The spirit of the season got into me, didn't it?
Pumpkin spirits more are mischievous than evil.
That's true. By the way, if you're clever with this, you can realize you don't actually have to do the math. No. You can actually guess the number up there pretty easily. Not here with me, but if you come with me to my office later, I can.
I'll just find one in another class.
Okay, folks. Is anybody still making valuable progress? Yeah? Okay. And don't forget, you can help each other. That is totally fine. Oftentimes, you actually learn more by helping or being helped by people around you. Every study ever actually says that people that are very close to you in skill level task are the best people to study with. Because their perspective will help you and overlap with you best. Okay, folks, we're going to have to move forward pretty soon here. So please go ahead and input your answer. Okay. I'm going to move forward, so input your answer. And we're going. Gone. Okay, so 83% said 331 degrees Celsius, and that is correct. That is most definitely correct. Okay, so how do we do this problem? Well, we gotta get temperature 1 into Kelvin, don't we? Okay, so 29 plus 273, that gives you 302 Kelvin. Okay. Now, up here on my slide shows, it's easier for me to solve variables first, because then I don't have to have a lot of like calculator pressing, right? Okay. And so I go ahead and solve T2 by itself, and I get the rest of it on the other side. I then input my numbers, so the 302 Kelvin, plug in the 3.2 atmospheres, that's that state 1, right? Or state 2, excuse me, right here. And this one here goes, this one here goes down here. Okay. And so the next part I have to do is, that is liters, that is not liters, is it? That is milliliters. So I need to get these both in the same unit. And so what is 0.180 liters in milliliters? 180. So I need to get that into milliliters. Yeah, it's times 1,000. Yeah. That's what milli means. Yeah. 1,000 milliliters per liter. Okay. And so I'm going to plug those in. 90 goes on top there. The 180 goes on the bottom there. I then go ahead and take my calculator, 302 times 3.2, divide by 0.8, times 90, divide by 180. That's going to give me 604 Kelvin. But is that the temperature that they wanted? They wanted degrees Celsius, didn't they? How do I get myself back in degrees Celsius? Yeah, I'm minus 273, right? Yeah, so 604 minus 273, which is 331 degrees Celsius. And that's my final answer right there. Okay. Anybody have any questions so far? Okay, fantastic. Okay, so Avogadro's law, this is the one that's actually going to relate moles. You probably could have guessed that because Avogadro, right? So what you're going to see here is the volume of a gas is directly related to the moles of that gas. V1 over N1 equals V2 over N2. Now, let me point out that we actually already knew this. What are you doing when you are increasing the capacity of your lungs, when you're moving that volume out, when your diaphragm is expanding? You're bringing in gas, right? You're bringing in amount of gas, right? What are you doing when you're compressing that diaphragm? You're releasing gas. You're moving gas out, aren't you? That's actually the purpose behind these, right? And so you've always been doing that to get in new oxygen and then release the CO2, right? You already knew this, didn't you? This is what happens when the temperature and pressure are constant. So if we go ahead and talk about gases, we have these temperatures and pressures that we have to talk about. This is going to end up needing a standard that we can evaluate things based off of. So we have the standard temperature and pressure. Okay, so the standard temperature and pressure. The standard temperature is going to be 0 degrees Celsius or 273 Kelvin. Anybody notice what that's the same as? Ice, right? That's the standard because you can make an ice bath in lab. So you make an ice bath and stick anything in it, and there you go. You got your standard, right? Why would we not try to use like room temperature, by the way? Are any of the rooms in this building the same temperature?
That's not exact.
Yeah. It's really hard to actually get to room temperature and stay there. Like if we were going to use something else, it would be 100 degrees Celsius boiling water, but that would cause us problems, right? Easier to make an ice bath. Okay, the standard pressure, that one is 1 atmosphere or 760 mmHg. That's because that is the at sea level standard pressure of this planet, right? If we were to have been on another planet where it was 2 atmospheres, this would have been 2 atmospheres, right? But we're on Earth, so. All right. So at the standard temperature and pressure, 1 mole of gas is going to occupy a volume of 22.4 liters. This is actually referred to as the molar volume. And so if you have a balloon that's full of 22.4 liters, that would actually be 1 mole of a gas. That's true for any of the gases all the time. Okay? It doesn't matter what the gas is, whether it's nitrogen, methane, hydrogen, doesn't matter, okay? They all end up having the same molar volumes. This doesn't really change. All right, this right here's that molar volume, 22.4 liters. And again, at STP, we're going to have 1 mole of each of those gases. Now keep in mind that a mole of a gas is going to have different mass, right? And that number for the mass is going to be on the periodic table. Okay? Now, this is actually why, for example, helium floats in a nitrogen-oxygen atmosphere. Because it is significantly lighter than the surroundings, right? Okay. Partial pressure, Dalton's law. I'm actually going to stop here because I don't want to introduce this in 1 minute and then you forget it. All right. You all have a wonderful day. Hopefully you have a great, fantastic Halloween.